Hello, I am Hassan Nassar. I will be presenting the paper TiVaPRoMi time-varying probabilistic row-hammer mitigation on behalf of my co-authors Lars, Bauer and Jörg Henkel. This is the outline of my presentation. First, I will give a short introduction about the row-hammer problem. Second, I will show the existing mitigation techniques. Then I will explain the concept of TiVaPRoMi and its implementation. After that, I will discuss the results and evaluate our work. Finally, I will wrap it up with the conclusion. So, what is the row-hammer problem? The memory controller periodically refreshes all the rows. The period between two refreshes of the same row is called the refresh window. The refresh window consists of multiple refresh intervals in which a subset of the rows is refreshed. That's where the row-hammer problem comes. The attacker induces disturbance to the memory rows. This is achieved by repeatedly activating the neighbors of the victim row until bit flipping happens. It's a powerful and easy to launch attack as it doesn't need software level vulnerability but uses memory access patterns. Now we look at the existing mitigation techniques. They are either software based or hardware based. The software-based mostly use machine learning to detect and stop the attacking program. However, it is slow, so bit flipping can occur before detection. Moreover, it can be surpassed using certain code patterns, and we will discuss the hardware-based more thoroughly as it is the category of our work. The hardware-based is mainly implemented on the memory controller level. In order to prevent bit flipping, the victim row is activated, which restores the charge level of the row. The hardware-based is divided into two classes, either counter-based, which in the most simple implementation has a counter assigned for each row. This has a high hardware overhead. Therefore, there were trials to reduce the number of counters using time-windowed counters or trees. But overall they all have significant hardware overhead. The other class is probabilistic, with each activation based on a probability the neighbors can be activated or not. It can be implemented simply stateless or to make educated decisions using a history table, but overall it has a high activation overhead. We will examine more the probabilistic subclass as it is the subclass of TiVaPRoMi. To show why it is needed. Let's say a DRAM with 2048 rows and has 128 refresh intervals. Row 12 is being attacked by repeatedly activating row 11 and row 13. Row 12 was last refreshed at refresh interval 0. We are now at refresh interval 127. The period between refresh interval 0 and refresh interval 127 is long, making row 12 vulnerable to bit flips. Then it needs to be activated. For stateless probabilistic techniques, with each activation for the aggressors, row 12 might be activated based on a static probability. For history table, the more row 11 and row 13 are activated, the more row 12 is promoted in the table. If it reaches the top, it is activated. Now we go to the same case but at refresh interval 1. Stateless and history table techniques will act as the same as at refresh interval 127. However, this time it doesn't need to activate row 12 as it was last refreshed very soon. This is where TiVaPRoMi and our contribution come. We use time-varying probability. Simply, the probability used to extra activate or not is a constant base probability of a small value times a time-varying weight, to take into consideration when was the victim row last refreshed. The simplest way is to have the weight as the difference between the current refresh interval and the refresh interval the row was refreshed. Going back to the example of attacking row 12, at refresh interval 14, the weight is 14 minus 0, which is 14. This is a low weight, leading to a probably having no activation. Now we move to refresh interval 115. The weight is now higher by 1 order of magnitude than at refresh interval 14, leading to a higher probability and most probably an extra activation is taken. Then we go to refresh interval 127, assuming that row 12 was activated at refresh interval 115. The weight is still high and an activation is very likely, although it is not needed as it was last activated a couple of intervals ago. This is why we use a history table to store when a row was last extra activated, leading to a corrected weight of 12 and a lower probability. Linear weighing is not the only way to calculate the time varying weight. We offer 4 techniques to calculate the time varying weight. TiVaPRoMi uses linear weight, so it has low extra activations but is slow to decide when to activate. LowPRoMi uses logarithmic weight, so it is fast to decide when to activate but has a higher activation overhead. LowPRoMi is a compromise between both. It uses a mix between linear and logarithmic weighing to lower the activation overhead but also take decisions more adequately. CES-KIT-Research uses the same logarithmic weighing as LowPRoMi times the number of activations of the aggressor per refresh interval. Extra activations are not taken then per each activation, but rather collectively at the end of each refresh interval. It combines both counter-based approach and probabilistic approach. Now we go to the implemented system. TiVaPRoMi is implemented as an extension to a DDR3 memory controller in VHDL. By tracking the activated rows and the refresh commands, it can function properly and issue the extra activations. The memory controller is adapted with rowhammer logic, which is similar to the refresh logic. TiVaPRoMi was evaluated through the following framework. Memory traces were generated using Gem5 and based on Spec CPU 2006 benchmark, attacking multi-rows using a typical attack code and a flooding attack to check for specific vulnerabilities. TiVaPRoMi and previous works are implemented in VHDL, and as seen from the figure, blue ones are the previous works, red is TiVaPRoMi. In the trade-off between area overhead and activation overhead, it is clear that TiVaPRoMi is in the middle, giving a good trade-off between both penalties. The table shows the comparison between TiVaPRoMi and the previous works. From the table, it is clear that when optimizing for resource usage, best candidate is LowPRoMi. When optimizing for activation overhead, best candidate is CES-KIT-Research. Now to conclude, we introduced the novel concept of time-varying probabilistic rowhammer mitigation. We have a good trade-off between hard-to-implement, counter-based techniques and probabilistic techniques. We have similar performance to the state-of-the-art tabled counters. We are able to achieve 27 times to 9 times reduction of the storage requirements compared to the state-of-the-art tabled counters and 12 times to 6 times reduction of the extra activations compared to the state-of-the-art probabilistic techniques. Thank you for watching.